Good morning. Yes, good morning. It is 11 a.m. here in Kingston, Ontario. This is MAE 106 Discrete Mathematics with Probability. My name is Richard Kohar, and this is lecture 16. And so we're going to start talking about some counting techniques. So we're going to start to get into combinatorics. And in today's lecture, we're going to be covering specifically the pigeonhole principle, multiplication principle, and the sum principle. Good morning. So, without further ado, here we go. Let's start off with me using that big word, which was combinatorics. And really, basically, it's the idea is basically it's a field in mathematics. So we have lots of things in mathematics. We have algebra, we have probability. Combinatorics is part of discrete mathematics, and it's concerned about counting. Kind of combinations of things, how many ways of doing or combining, configurations. And the idea behind this is not to be able to brute force it, but come up with some more elegant ways of counting without actually having to do it. So So just thinking of ways of counting without having to resort to brute force. And I mean, like, for example, like if I had these pen caps here, how many ways could I organize these or line these up? Well, instead of me going, okay, I can have it like this and this, that's one way, and then I can do it like this way, and there's the second way. There's actually faster ways of counting things like that. How many ways can we line up those pen caps? So that's just an example. But we'll get to principles that will handle that potentially in this lecture or in the next one. So that's section 5.1, and we're going to be covering the pigeon principle. So it's quite an easy principle to follow along. The idea is that let's say let's say I have 3 boxes. These are like pigeonholes. So I have 3 pigeonholes. Okay. And let's say that I have 3 pigeons. I don't have a pigeon stamp, but let's say I have 3 pigeons. Three pigeons. So what I can do is I can put 1 in each box. 1, 2, and 3. So 3 pigeons, 3 pigeonholes, that's easy enough. But what happens now if I have, let's say I still have 3 pigeonholes, oops. Let me draw this a little better. There we go. So instead now I have 1, 2, 3, 4 pigeons. But I still have 3 pigeonholes. So if I'm going to do that, I can put 1 pigeon in each. But what do I do with the 4th one? I could put it here, I could put it here, or I could put it here. I'll put that one there. Because I have 4 pigeons and 3 holes, there will be at least 1 hole that will have 2 or possibly more pigeons. And that's the concept of it. I know it sounds really easy, but yes, there will be at least 2 or more. There will be at least 1 hole with 2 or more pigeons. And the max that we could do is we could move all these pigeons inside of 1 box, and so you could have like 4 pigeons in one, but that just means that there is at least 1 hole that will have 2 or more. So seems reasonable enough. So the pigeonhole principle, kind of using these ideas, I'll just kind of formalize it. So that's what we do. Pigeonhole principle. So again, we'll formalize this. We can say that we're going to say that we'll say n is a natural element. So if there are n plus 1, so 1 more object, more than boxes, so n plus 1 objects placed in n boxes, then there's a box with at least 2 or more objects. Okay, so that's the pigeonhole principle. So if I wanted to do some sort of proof, and I will just explain it more in words. So let's say I have I'll just make some boxes here. Okay. So let's say that I have n boxes. Okay. And let's say that I have a whole bunch of, there's a lot. Let's say that there's n objects. Then what we can do is we can fill each box with one object. So we can put in one in each. So there's one, there's another one. And we can keep filling that box until we get to the end. And so there's n objects. Okay, so one object in each box. So now we have one more object. So we have another one right here. So that's the there are no more empty boxes. So it must go in one that is occupied already. Okay, and that's it. So it could go at any one of them. Now, if you thought, that's kind of the end of the proof. Just as a little bit of a remark, you thought, okay, well, maybe I didn't have to put one star in each box. Let's say that I have piled it up, well, so that there was one box empty, but that means, so if you don't initially put one object into one box, then there would be definitely a box that has two objects. And so you would already satisfy then the condition or what we were trying to prove. Okay. Is that pretty clear about the pigeonhole principle? It was named after a German mathematician by the name of Dirichlet, and he came up with the idea in the 1830s. And basically actually comes from an older German word, and it was referring to kind of like the wooden partitions that were kind of in secretary desks, old style writing desks, and they were kind of filled with slots, and people would put letters into it. So this is kind of what going to motivate this example then. So let's have an example. So let's say that we have our letter carrier, and he has 10 letters for our department. And he's going to place them in a communal mailbox that has 9 compartments. right? Then we know for sure, therefore by the pigeonhole principle, there is a person who will receive more than one letter. It is a fancy method. Yep. What other things could we think about in terms of, so this, let's say this is example A. Here's another one. Let's say that you have a group of a cohort of 366 students. Then at least 2 students will share the same birthday. Right? Because same idea, by the pigeonhole principle, you have, let's say, assuming a year is 365 days. If everyone has 365 unique birthdays, well, that 366 student or person is going to have to be placed somewhere in that calendar, in those boxes, those days. And so it'll have to share at least with one other student. Okay, what's another example of the pigeonhole principle? Here's page 3. Let's do C. So let's say if you pick 6 numbers, and we're going to say from the set 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's do up to 10. So if you pick 6 numbers from there, then two of them must sum to 11. Okay, so how could we prove that? Is that every number can be paired with another to sum to 11. And there's kind of 5 pairs that we can do in that. So you can have like 1 and 10, so that gives you 11. You can do 2 and 9, and we just kind of decrease and increase in the second digit. 5 and 6. And that's it. Okay, so these all equal to 11. So if I did 1 plus 10, that's 11. 2 plus 9. Okay. So each of the 6 numbers you picked must belong to one of these pairs. So notice that if you pick 6 of these numbers, so for instance, like I picked 1, 2, 3, 4, 5. So for example, then the 6th number has to be from the set 10, 9, 8, 7, 6, and any of those will work with that previous set that we had picked. To sum to 11. And that's it. So therefore, by the pigeonhole principle, 2 of those numbers that you picked must be from the same pair, which by construction sums to 11. Pretty cool. So now we can move on to 2 other fundamental principle counting techniques. So what does that mean? We got the multiplication principle and the sum principle. So the multiplication principle so I think the example that I have in the book is, let's say that we were going to purchase a MacBook Air. Oops. There we go. A MacBook Air. And it has, for the display, let's say that there's 13 inches and, I don't know, let's say 15. And we'll go with an SSD. Let's say that it has 256 gigabytes and 512. I always think of dice probability with examples like that last one. Yes. And this is why it's important. We're going to start talking about counting sets, and then we're going to get into things like probability, where it is about counting all the possible outcomes or configurations or the combinations. So we will get to that. So so we have 2 choices here. And we have 2 choices for this one. So I can run through all the possibilities. This could be a brute force. I could have 13 inch with a 256. I could have a 13 inch with a 512. I could have a 15 inch with a 256. I can have a 15 inch with a 512. So if you noticed what I have done, really, so just kind of labeling these all out. There was 4 possibilities. Abilities or choices of purchasing this through the site. But what we can actually do is we can start to think of this as like a grid. So we had a table that we had done nicely. So down this column is 13 inches. And down this column was 15. And down this row that we did 256. And we did 512. So we can enumerate all these possibilities. So what we have seen here is we've got basically a table that was the number of entries that are in that table is I have 2 for this one and 2 over here. And because we've got kind of this grid, there was 2. Oops, maybe I'll use some color then. So then it was really, I had 2 choices for the first one times 2, which gave me 4. And that's really what the multiplication principle is about. So if I generalize this, come on. I wanted to generalize this. If the first, now they say first task. So if I said the first task has N1 outcomes. So again, we're being very general when we're saying task. So for this one, it could be like the task could be selecting a display. So the first task in this one would be picking a display, and there was 2 choices. So in this case, it would be 2 outcomes. And no matter the outcome of the first task, the second task we'll say has N2 outcomes. So what am I doing here? I'm just being very specific, saying that, okay, so I picked my display. I had 13 inches or 15. I picked one of them. And that this does not affect or limit my selection for the second task. Okay. Then the two tasks performed consecutively, so meaning one after another. Consec. Utility. Oops, that should be C. Have n, so n1 times n2 outcomes. Okay, that's a lot of formalism, just so that I can do that. But that's what the idea is. And the proof is very similar to what we did previously. It's just generalizing. So if you had some sort of table, let's say we had a, we'll call this B, C, dot, dot, dot. So up here, we had N1 outcomes. I had N2. Then the number of possibilities is just multiplying them. Okay, and that's it. So you can think of it as, you know, here's the first one, A, here's B, A. So that's just a way of enumerating all the ways. That's it. Now, can we extend this? Yes. It gets a little bit more trickier, but so instead of working in 2 dimensions, now we'll be working in 3. So let's say that I have N1. So here will be N1, here's N2, and then I'm going to go in this direction here. Here's N3. So now instead of working with little cells like we would have in a spreadsheet, now we're kind of working with these ideas of cubes. So that would be one possibility, and then here's another one, so on and so forth. So yes. So if you had 3 tasks, then it would be N1 times N2 times N3. And if we keep going further, if you had, let's say R tasks, so R many tasks. If you had R many tasks, then you would have N1, N2, N3, dot, 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 all the way up to NR. But that's what we do all the time in math. We're trying to, we think with a simple problem, like what we did right here with maybe 4 possibilities, and we keep extending it further and further and further. I don't have a stencil for that. I wish. I've got just the circle stencils here. I'm sure I could find something. All right. So, for instance, let's do, let's extend that. Let's do continued. Let's say that, okay, so I had a MacBook, and let me just pull that sheet back. I had a display, oops. So we had a display. We had 13 inches, we had 15 inches. We had an SSD, which had 256 gigs and 512. And then let's say that you can change the keyboard. So you say we could have it in English. We could have it in French. We could have it in German. Let's say 3 possibilities. There's many, many languages you can change the keyboard to whatever you want, but let's say 3. Then the number of configurations is we have 2, and we have 2 for this one, and last we have 3. So we'll have 4 times 3 is 12 different configurations. Okay, we can do coin flipping. So let's say that my first task flip a coin. The second task, flip it again. Third task, flip it again. Okay. So, what does that mean? Well, I could have, okay, so I'm tossing a coin 3 times. So I can have toss 1, I can have toss 2, I can have toss 3. So again, it could be heads or tails. I could have heads or tails again on the second toss. And lastly, so there's all the possible ways of doing it. You can enumerate them that way. So this is kind of the brute force method. I sure wish that there would have been an easier way to do this. And wait, we just did this. So those are all the possible outcomes right there. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 outcomes. And this is what we'll call kind of the brute force method, where we have to come up with a diagram or a tree, and we're counting literally every single possibility. But with the multiplication principle, because the coin isn't affecting what we had done previously. Flipping the coin doesn't mean like I'm going to lose. This second task is going to affect the first one or the third one. It doesn't. So by the multiplication principle, it's 2 times for the first outcome, 2 times for the second outcome, and there's 2 for the third one, which gives us 2 to the 3 or 8. Yes, exactly, 2 cubed. Okay, so how about this? Now it's the sum principle. Okay, so let's say that there's a student and she is deciding to go on holiday, and she's either going to go south or up north. So let's say that her budget only allows for her to go visit Montreal or So we have a student. Let's say she's going to go on a holiday or break, and she can go north. She can go either to Toronto or Montreal, or she can go south and she can go to a Myrtle Beach, which is, I believe, in North Carolina. She could go to Cape Cod, which is in New England, Massachusetts area, and New Orleans, Louisiana. How many ways can she go on holiday? Well, with the sum principle, these two things are not affecting each other. Okay, so in this case, she has 2 possibilities for this one, or she could do 3. So if she goes north, that's picking, if the outcomes stay constant, heads or tails can be done as x to the n, where n is the number of tasks and x is the number of outcomes. Yes, for multiplication. So the question is kind of extending that. So if I had, so here's the question that was kind of asked. Let's think about that for a die instead. So if I had a die, which is kind of that cube with dots on it. So there's 1, there's 2, 3. A die has 6 sides or 6 outcomes. And if you roll it, three times, then what you would get is 6 times 6 times 6, or that's 6 to the cubed. And I believe, sorry, typing on the phone. And I believe 6 cubed is 216, right? I'll double check that. Yep. So yeah, you have the x is the, so you can think of it that way, if that helps. Okay, how many ways can she go on holiday? Well, she can pick either going north. So if she goes north, there's 2 possibilities. Or she can go south. Now notice that this is the exclusive or. She can't do both, right? This is quite like she's picking one or the other. It's not like she's going to go north and south. So when we have that, we have 2 plus 3, which gives us 5 outcomes. What if we say that we can't have the same number again? Would it be 6 times 5 times 4? Yes. That's right. But that's a different counting principle. Actually, that's not. We'll get into that into the next lecture. Okay. So that just kind of illustrates this. This is kind of important. Is the or. So you could go north or south. Whereas with the sum principle, you can think of it as adding, which is the sum. And with the multiplication principle, going back to this, I picked a display, and with the multiplication, it's and I choose the SSD. Okay. Okay. So we'll just kind of finish off then the sum principle. If the first task has n1 outcomes, and the second task has n2 outcomes, and they can't be performed simultaneously, so then there's n1 plus n2 ways in which the first or the second task but not both can be performed. So there's the sum principle. So we just add them. Okay, and that can also be extended for are many tasks. but we will have to stop there for today. Thank you everyone for tuning in for this lecture 16, the Pigeonhole Multiplication and Sum Principles. I'll post the scans of these on the Moodle website, so if you didn't feel like writing out all of that today, you are more than welcome to download the PDF of this. Thank you everyone for tuning in, and I will be sending out an email soon, and hopefully the YouTube is finished processing the video. I thought it would be a little bit quicker. So again, thank you very much, and have a great afternoon.